Okay, so lab we're doing today, guys, is to look at mechanical energy conversions, to look at work energy theorem, okay? Because we've done everything thus far assuming that all the things we look at happen in the perfect physical world, okay? We need to do a lab to see how it works in the real world, all right? Because we've always said that whenever you do work, that's the energy that'll be in that system, and it's always the same number. In reality, is that the truth? And far from it. Okay? Energy conversions, especially mechanical energy conversions, are incredibly inefficient. Okay? Energy is lost whenever one form of energy is converted to another. All right? We're going to be looking at a lab here that's going to set up like our work lab, okay? Where we're going to pull back the rubber band, but this time we're going to put a cart in it. Okay? And we're going to convert the work we do into potential energy in the rubber band, just like we did in the work lab, okay? And we're going to convert that potential energy into what? If we let this thing go, what's going to happen? It's going to move, right? So it's going to turn into kinetic. So what we want to find out is how much of the work we do actually ends up being kinetic energy in the cart. Okay? And I think you'll be surprised just how little of that actually gets through. All right? How much energy is actually lost along the way. All right? And part of the thing you're going to need to think about is, where can some of that energy go? Okay? Where did it disappear to? What happened to it? Okay? So have everybody in your group kind of watching and observing, okay, where they think that energy might go during the experiment. Okay? So the problem we're investigating, how much of the available potential energy is converted into kinetic energy in a mechanical energy conversion. All right? Now, our variables. Okay? What are we manipulating in this experiment? What's the thing that we are actively controlling or putting into it? Yeah, or work. Yeah. Okay, one or the other. Right? That's what we're doing initially, is we're doing some work, right? That's where this whole experiment comes from, is from the work that we do at the very beginning. Okay, now, the other ones I want you to think of. Okay, what's going to respond to that? Probably has something to do with what we're trying to convert. Okay, and then your controlled variables, anything that's going to be the same between all of your trials. Probably a lot of those will be similar to your work lab. Okay, as this sets up very similar to that. So in terms of controlled variables, lots of similarities. Obviously, responding and manipulated are quite a bit different for this lab. Okay, for your hypothesis, okay, we want to generate a hypothesis, tentative answer to the problem. Okay, in the if part, should we talk about work energy theorem a little bit? And maybe what it says about conversion of energy? I would think so. Okay, the if part should probably say, you know, something, if the work energy theorem says something. Okay, you tell me what. Okay, and then describe this experiment. In the then part, tell me what should happen in the perfect physical world. Because if you're going to say the work energy theorem says this, then in the then part you have to say what's going to happen according to that. Which means our hypotheses are probably all going to be wrong. Okay, is that all right? It's absolutely fine, as long as in your conclusion you explain why. Okay, I'm not throwing you under the bus here. I'm not trying to set you up for failure. You will not lose marks because you say something in your hypothesis that's not right. Okay, as long as in the conclusion you say what happened and what was right. Okay, everyone follow me there? All right. Okay, so there's a lot of variables that we need to record. Okay, I don't have the chart. Well, I have the chart here. I'll show you it next that you're going to use. It just didn't come over into your Google Doc. I have to fix it before I put the assignment in Classroom. So some things we need to know. For potential energy, you can cross off mass of the cart. We used to do this lab slightly different, and I changed it because it worked better this way, and now we don't need the mass of the cart. So you can cross that off. I just forgot to take it out of there. Okay, so potential energy, we need to know the force that's being applied, and we'll measure that with the spring scales. Okay, we need to know the distance over which that force acts, and we'll measure that with the rulers. Okay, no problems there. Kinetic energy, again, cross the mass of the cart off. We're doing this differently. We don't have to worry about the mass of the cart. Okay, the distance traveled by the cart, okay, after its interaction with the elastic. That means don't measure how far you pull the cart back as part of the distance. Okay, everyone follow me there? We only are worried about the kinetic energy of the cart after all of the work has been done. Okay, so that is after it leaves the rubber band. And then the time of travel. So one of you is going to have to use the stopwatch on your phone, okay, to time it. So basically when you say go, start your timer, because by your time your reaction time is all done, it'll be off the rubber band and you'll all be good. Okay, time it until it rolls to a stop. Now, I'm going to have you do 4 good trials. You'll probably have to do 8, okay, in order to get 4 good ones, because these carts, if you don't pull them back just perfect, they spin out, okay? Or they go crazy off to the side. And it takes a little while to kind of get the technique down as to how you can get these things to shoot reasonably straight, all right? So the best way to get them to go reasonably straight, okay, is to pull back, okay, from the sides with the rubber band across the back here. Okay, if you put the rubber band up here, it's on these wheels, and all it'll do is spin the wheels. It'll do a big wheelie and flip over onto its top. Okay, so you want the rubber band to be across the back here, okay, when you pull, and then let it go by just releasing from the sides. I have a lot of people who try and pull back from here, but then inevitably, as they let go, it flips up, okay, and just flips over top of the rubber band, and nothing happens. Okay, so the best way is to pull it back from the side and just release it that way. Everybody with me? Okay. And again, it's going to be tough. You're going to have to try and get it to go fairly straight. And what you're going to want to do is we're going to have to move the desk quite a bit, and you're going to want to shoot them kind of between the rows because you need a fair amount of space. It can't hit anything before it coasts to a stop. You guys with me there? And inevitably, once in a while, a group gets a great trial, and the thing's rolling and rolling and rolling. It's just about to stop and it hits the wall or the desk or whatever. So that's what you're probably going to do a few trials before you get them to work perfectly. That's okay. Okay, just record the ones that worked right. Everyone with me on that? Okay. All right. Now, so those are the values we're going to record. Okay. There are several values we're going to have to calculate, and it tells you exactly how to do that here in the procedure. Okay, so in the procedure here, we need to calculate the acceleration of the cart, and here's why we need the acceleration of the cart. Okay, work is force times distance. Agreed? Okay, here's the only time you're going to use this formula that's on your formula sheet. It's the only time you're ever going to use it. On your formula sheet, you have this formula. This is Newton's second law. Force is mass times acceleration. Okay. Oh, right. We still need the mass. Uncross that. Totally forgot about that. We still need the mass for this part. Okay. But I'll tell you what the mass is because all these carts are exactly the same. All right. So we're going to go mass times acceleration. Now, we're calculating the acceleration using some of the stuff we're going to measure. Okay. And that is the distance the cart travels and how long it takes to do that. Okay, 2 times the distance divided by t squared will give you the acceleration of the cart. It's a formula you'll learn in Physics 20, okay, but it's the easiest way for us to do this lab and get good data, so that's the formula we're going to use. You'll never be tested on that formula in Science 10. It's just to do this lab with. Okay. All right, so we'll use that, and that will help us to calculate the force of friction. Okay, and that force is what is doing all the work that's taking the kinetic energy from the cart. Everyone follow me there? Okay, so when I release the cart immediately, once it's off of that rubber band, is starting to slow down. And it's starting to slow down because its kinetic energy is doing work against friction. Okay, so by the time it stops, it's lost all of its kinetic energy to friction. You guys with me there? Okay, so if I calculate how much work is done against friction, that helps me know how much kinetic energy the cart had, because it is impossible for me to use this formula in this experiment because I have no idea what this is. When that cart comes off of that rubber band, I have no idea how fast it is going, and I have no way to find out. Okay? There's no way for me to measure it. Okay? There's no way for me to, record it or anything like that. So we have to use this other method where we use the work done to slow the cart down being equal to the force of friction. That's the law of conservation of energy. Agreed? Okay? Whatever energy we had at the beginning, we have at the end. It's just doing something else. Okay? It's doing work against something else. All right, so obviously, yes, we can't use that formula, so we're going to use this. That'll give us the force of friction times the distance. And then we'll know how much work was done against friction. So that'll give us, okay, the kinetic energy of the cart. All right, and it talks about all of that down here in the analysis, guys, but just to remind you, okay, so kinetic energy, okay, says here, since friction does all the work on the cart and represents the force that uses all the kinetic energy, we can say that kinetic energy equals work. The work done against friction is mass times acceleration times distance. Okay, for our potential energy, we're simply going force times distance. So your spring scale reading, same as before, by the way, you got to divide it by 100 to get it in newtons, okay, multiplied by the distance, okay, that you pulled it back in centimeters or meters? Meters. All these distances need to be in meters, okay, keep that in mind. All right, so yeah, all the distances, right, in meters, okay. All right, so procedure, like we said, we already talked about how that's going to go, okay, release the band carriage system. Now, do you need to, in the picture here, they show the cart being pulled back with the spring scale. Is that a good idea? It is not, because the spring scale will go flying. Okay, so what we want to do is just on the first trial, hook the spring scale around the back wheel of the cart. Okay, just hook it on here on the back axle, pull it back, okay, a certain distance, however far you want to go. Okay, however far seems reasonable. Okay, and you're going to use that same distance every time from then on. In fact, what you might want to do is just put a little mark on the floor, okay, and then the next time with just your hands, pull the cart back that far. Okay, everybody good with that? Yeah, because you can't do it that way. That's just to get your initial force reading. You're going to use the same potential energy on all the trials. We're not changing that. All right. Okay, and then for the analysis, okay, there's no graph on this one. Okay, there's no graphing on this lab, but you do have to show me your calculations. They're not difficult calculations, but you do need to show them to me. Okay, calculate the work done in pulling back the rubber band. Show your work. Did it tell you how to do that in the procedure? Yes, it did. So just follow what it said in the procedure, force times distance. Okay. For number 2, calculate the acceleration of the cart using distance and time. And it says here, see initiating and planning step 2. It tells you that's that acceleration equals 2d over t squared. Okay, that's what you're using here. Okay, this is force times distance, this one. All right, calculate the kinetic energy of the cart. Okay, that was this m times a times d thing, all right, that we were going to do. Okay, outline how you determined the potential and kinetic energies of the system. So you got to explain a little bit here. Okay, how did we figure out? It's kind of what you're basically going to be saying in your own words what it said in the procedure. Okay, the potential energy came from us doing this. The kinetic energy was calculated by figuring out this amount or whatever. Okay, and then number 5, did the potential energy of the system equal the system's kinetic energy? Why or why not? Okay, suggest reasons for your results. That's where I was saying you have some qualitative observations you're probably not writing down that your group might have that help you determine where some of that energy went. Okay, so listen, feel, watch, okay, for those kinds of things during the lab. Okay, then as usual, restate your hypothesis and explain why you reject it in this case. Okay, and identify any sources of error, suggest improvements. Those could probably be similar to your work lab. Okay, there should be similar sources of error there. And again, you don't have to do the class discussion. Okay, we'll do those when I hand them back. Now, your chart, I'm going to put it into the lab report for you. I just have to redo it here. For some reason it didn't come through right. Okay, so I'll put it in and it'll have all of these spaces. They'll all be blank. Okay, this is just class data from another time that I didn't delete. Okay, so it gives you some idea about how far everything is. I think they used 4 newtons and 5 centimeters or something like that they went back. You'll probably use something different. Okay, and that again is up to you. What did we notice though in the work lab if we started pulling really far? Did the relationship stay linear or did it start to curve? Yeah, it started to curve. So keep that in mind. You don't want to overdo this. Okay, it's not a contest to see whose cart can go the farthest. Okay, in fact, this lab tends to work best if you don't overstretch the rubber band. Okay, so set your chairs up about the way they were before, and don't pull it too hard, and you'll probably get better results. That, and the further it goes, the more chance it is it hits something and you have to redo the trials. Right? So shorter distances of travel are probably best. Right? Again, don't write these numbers down, guys. Your numbers are going to be different. Okay? So you'll fill all these things in. So for each trial, you'll have a distance and a time and an acceleration, and you'll average those numbers. Okay? For the EP, since that number's the same for every trial, you don't need to write it in every one of those. Just write it once down here. Okay? The kinetic energy, all right? Okay, figure it out for each one, okay, and, or sorry, you don't need to do it for each one, just use the averages down here. Okay, you'll have your average acceleration, mass times acceleration times distance, just do it once down in here. So, okay, these ones here, you can just cross off, okay, maybe I'll put X's in them or something, but you won't have to fill those boxes in, you'll just have a final number there. Okay. Questions? The mass is 0.05 kilograms. Okay, these are 50 grams each. Any other questions? All right. Each group, when you're measuring the distance your cart goes, okay. Obviously, if it turns a little bit, if it's just a little bit, that's okay, right? Measure in a straight line to where it ends. So if that's diagonal from where you are, that's fine, okay? Measure it along there. Make sure you use the metric side. And since you're probably only going to have 1 meter stick, okay, you'll have to put it down and then mark where it is and then move it again like that, okay? What I would say is, to be most efficient, what you might want to do is just grab one of these dry erase markers, okay, and mark where your carts go on all of your trials and then measure them all at once. Okay? When you're done though, you have to come get the board juice and spray it and get those off the floor. And you have to scrub kind of hard. Okay. All right, have at her here, guys.